This is project 23118, and this project involves in-house foam parts production for hydronaulics. Now it's time to meet the group. My name is Dallin Graybill.
I'm Sophia Mishke.
I'm Jamie Scott.
And I'm Chandler Canay, and welcome to our video presentation.
We are the in-house foam part production team, and we are working with Hydronaulics and Dr. Greg Ogden.
The primary objective of this project is to create a foam to replace EPP foam inside unmanned surface vehicles, which will have desirable manufacturability, cost, and material physical properties.
The project criteria and constraints include manufacturability or ease of production, throughput as in how many large parts can be made per day, cost in comparison to hydronaulics' current manufacturing cost, density, tensile strength, abrasion resistance, UV or environmental resistance, water absorbance, and buoyancy.
Hydronaulics currently uses EPP foam, which is expensive and difficult to manufacture, but it is durable and lightweight.
In our initial research phase, we discovered hundreds of potential solutions. We first narrowed this down by, per the preferences of hydronaulics, excluding foams which require large and costly foaming machines. Then, through further research and collaboration with Dr. Douglas Loy, we narrowed down our selection to polyurethane foam. We then decided to try two different polyurethane production methods, a two-part polyurethane kit and a custom formulation using raw materials.
Polyurethane foams are made by reacting polyols and isocyanates, along with other reactants for different foam properties. The polyurethane foams used in this experiment were a two-part foam kit and a custom foam formulation. To make the foams, wooden boxes were made and silicone was cast around a 3D printed part. Once the mold cured, the components of each foam type were reacted within the mold, and these foam pieces were used for mechanical property testing.
Here are the finished silicone molds, one for the cube and one for the dog bone foam shapes.
Here we can see an early trial run of the two-part foam production. First we measure out the B-side liquid, then the A-side liquid, then the two are combined together, mixed, and added to the silicone mold.
The picture on the left shows how the pressurization of the foam looks, and the picture on the right is the final product of the foam kit formulation.
The B side of the custom formulation was made by adding water, DMCHA, PTMEG, and surfactant to a clear cup. This mixture was then thoroughly stirred and left in the fume hood to off-gas for 2 minutes.
Here the MDI solution is added, which reacts with the polyol exothermically. During the reaction, the mixture expands, releases energy, water vapor, and CO2, and then solidifies. After the mixing here, on the video on the left, the video plays in real time. You can see that it takes about 20 seconds to complete the reaction after the mixing is complete. On the right is a side view of a trial run that illustrates the complete reaction.
The optimized foam formulation was used to produce samples in the cube and dog bone molds with minimal spillover.
Here you can see how we completed our abrasion resistance testing. The first step was to record the initial mass of the cube. The next step was to insert the cube back into one of the silicone molds. The bottom of this mold was filled with additional silicone so that the top of the cube would protrude. Then a cheese grater weighted down with a brick was placed directly on top of the foam samples. 10 complete back and forth motions of the cheese grater were completed. The cube was then removed from the mold, dusted off, and its final mass was recorded. The parameter of interest here was mass lost due to abrasion.
As for the impact test, the hammer sits in a resting position, which is approximately 180 degrees from its striking position. Once the apparatus is stabilized from the back, the pull pin is taken out, which allows the hammer to convert potential energy into kinetic energy and strike the test foam piece. The hammerhead strikes the foam piece at a constant area and force. The video shows indentation of the foam kit and lack of indentation of the EPP and custom foams. Here's the setup for the UV test. One EPP sample, two kit samples, and one custom foam sample were placed outside for this test.
Here you can see a time-lapsed example of tensile testing on a tensiometer provided by R3 Aerospace. In this example, an EPP dog bone is pulled apart. To complete buoyancy testing, we placed our cubes in water and left them for 24 hours. If the cubes were still floating by the end of the test period, that was a pass.
Water absorbance was tested by weighing each sample when dry, then submerging the samples under water with a bucket lid for 1 hour, and then patting the excess water off the outside of the samples and reweighing them.
Here you can see the results of our foam formulation iterations. The formulation for iteration number 9 is pictured. This formulation resulted in the foam with the most uniform cell size, so we used it for making our test samples.
The density of each foam formulation was calculated by measuring the mass of a foam sample of known volume, and the averages are shown.
Here are the results of the impact test. Only the foam kit produced an indentation, which was on average 1/4 of an inch.
Here are the results of our tensile testing. The custom foam performed the best, requiring 65.57 psi for it to pull apart.
The foam kit performed the best in abrasion testing as shown by the minimal lost mass, followed by EPP, while the foam kit performed the worst.
The buoyancy test was measured on a pass-fail system, where floating for a prolonged period of time is considered to be a passing score. While all foams passed this test, the custom foam sample was slightly submerged due to water infiltration in some areas where the foam had more open cell characteristics.
The foam kit was the most water resistant, gaining the least water weight. The EPP performed the worst, over doubling its mass with water weight. The large increase between 1 and 60 minutes also indicates that the water is absorbing into the cube. The custom foam did not absorb any more water after the initial minute, so the absorbance is simply due to the incomplete skin.
Yellowing was observed on both of the polyurethane foam types during UV testing. Whether this yellowing will affect the material properties will be determined in material properties testing.
Here is a PFD that represents the scaled-up process of our custom foam production. All components except MDI are fed to a primary mixer, then mixed, then sent to a secondary mixture with MDI. From the secondary mixer, the mixture is sent to a molding tank where it will react and cure and become a finished foam part. The main hazards realized during testing include pipe/mixer clogging, overpressurization, and heating requirements. The possible solutions to these problems include finding an optimal secondary mixer location, creating a relief opening, and adding heating coils to the specific tanks.
The EPP foam currently used by Hydronauts costs about $75 per part to produce. It is estimated that either the foam kit or the custom foam would reduce this cost by over threefold. Based on these experiments, an optimized custom foam is recommended to Hydronauts. The custom foam was more durable than either the foam kit or the EPP. It is also cheaper and easier to produce than EPP. However, the custom foam is too dense for Hydronauts' applications, so further optimization is required. Further research into product accumulation in the automated scaled-up process and further formulation optimization are recommended.